Fine. Greetings. So, welcome to today's class. So, we will continue from where we left off in the previous lecture. Like in the previous lecture, we were discussing about different types of suspensions. So, and we stopped with a discussion on independent suspensions. So, today we will look at various common realizations and configurations of dependent suspensions. Okay. So, the first dependent suspension that we would be looking at is what is called as a solid axle leaf spring suspension. Okay, that is the first configuration that we will look at. So, this is very popular particularly on vehicles like where the rear wheels are driven. Okay, so you can see this propeller shaft just splitting the drive torque between the left and the right wheels through the differential unit. And here like we have a solid axle, right. So, this is our drive axle, and what happens here is that like the leaf spring like are clamped to the axle, and we can see these eyes which are then attached to the vehicle body. Okay. And there is also a shock absorber that is provides damping to the vibration levels. Okay. So, this is very common, pretty popular independent suspension. So, we can immediately observe that the leaf springs are clamped to the axle, okay, and their other ends are attached, and their ends, right. So, are attached to the vehicle body. So, that is a solid axle suspension. So, now we can observe that the leaf spring also provides some sense of support like to the suspension with respect to the vehicle body along the other directions, right. So, because since the ends of the leaf spring, the eyes are clamped to the vehicle body, it provides some support along the longitudinal direction, right. So, that is a feature of this particular configuration. So, the leaf spring also provides a reasonable support to the suspension, okay, along the longitudinal and lateral direction, right. So, in a certain sense, if the axle tries to move with respect to the vehicle body along the lateral direction, there is some stiffness, right, to essentially prevent that. Okay. So, longitudinal / lateral directions. Okay. So, that is one advantage. So, of course, these leaf spring suspensions are simple and economical, but however, due to the presence of a solid axle and the spring itself being significantly heavy, right, these suspensions are heavy, right. They result in higher unsprung mass, okay, and this results in issues with ride quality and handling characteristics. Okay. So, these are some issues with solid axle leaf spring suspension. Okay. Yeah. The next type of dependent suspension that is commonly used is what is called as a solid axle coil spring suspension. So, in the case of the solid axle leaf spring suspension that we just discussed, the suspension stiffness is provided by means of a leaf spring. In this solid axle coil spring suspension, the leaf spring is replaced with a coil spring. So, that is the main difference in this version. So, this is also a popular dependent suspension. So, as we can observe, so this is a rigid axle and we can observe that there is a coil spring that provides the compliance in the suspension and there is a shock absorber which also serves to attenuate the effect of road disturbances, right, and help in energy dissipation. So, in a coil spring suspension, since the coil spring can typically give support only along the axis of the spring, we require additional elements such as control arms to provide support along the longitudinal and lateral directions. So, a control arm is typically used in a solid axle coil spring suspension to provide structural support. So, let us summarize a few important points of a solid axle coil spring suspension. So, here as we discussed, coil springs replace the leaf springs. However, since the coil spring provides support only along its axis, typically control arms are used to provide structural support along the longitudinal and lateral directions. And these control arms connect the solid axle to the vehicle body. Okay. So, that is how they provide the structural support. So, this is the coil solid axle coil spring suspension. Another popular category of a dependent suspension is a beam axle suspension. So, this beam axle suspension, the schematic of which is as given here. So, one could observe that there is a beam on which the spring and the shock absorber are mounted, and such a beam axle suspension is commonly used on the rear of front wheel driven cars. Okay. So, this is the beam which connects, which lies in between the two wheels, and we can see that there is a coil spring and a shock absorber. And typically what are called as trailing arms are provided on the beam axle suspension that connect the beam to the vehicle body, so that like structural support is provided in the longitudinal and lateral directions. And we can also observe another component which is termed as the Panhead Rod, which we will shortly encounter, but the Panhead Rod serves to improve the roll stiffness of the vehicle. So, for example, when a vehicle takes a turn, there is what is called as lateral load transfer from the inner wheels to the outer wheels. Then in order to ensure that the vehicle body does not roll significantly, we need to use elements like the Panhead Rod to improve the roll stiffness of the vehicle. So, that is one important function of a Panhead Rod. In the case of independent suspensions, we will shortly see that the same functionality is achieved by means of what is called as a anti-roll bar. An anti-roll bar is typically used in an independent suspension to improve the roll stiffness, such that when the vehicle takes a turn and there is a load transfer from the inner to the outer wheels along the lateral direction of the vehicle, the body does not roll significantly. Okay. So, that is a very important action, and the anti-roll bar which is used in independent suspension also ensures that when there are disturbances from the road, the two sides can move with certain degree of independence with respect to each other, and that independence does not affect the contact between the tire and road. The anti-roll bar will take care of that aspect also, which we will see shortly. Okay. The beam axle suspension is commonly used in the rear of front wheel driven cars, and the vehicle body is connected to the beam through springs and shock absorbers. And trailing arms are used to connect the beam to the vehicle body. To provide support along the longitudinal / lateral directions. Okay. So, that is a beam axle suspension, which is also a commonly used dependent suspension. Now, a few other elements in the suspension, okay, are as follows. So, we have what is called as an anti-roll bar or a stabilizer bar or sway bar. Okay. So, what is this anti-roll bar? So, this anti-roll bar, as the name indicates, it provides some resistance to roll motion. Okay. So, and where are they used? Typically, as we discussed, when we have an independent suspension, there is some what to say flexibility available, like to ensure that a disturbance which is felt by a wheel on one side is not transmitted to the other side. Okay. So, this is an independent suspension, and we can immediately observe that the disturbance which is, let us say, felt on either side, is basically attenuated right before it reaches the other side. The anti-roll bar essentially ensures that while this disturbance from side to side is attenuated, the roll resistance or the roll stiffness is not affected. Okay, so that is the function of an anti-roll bar. Okay, so what this anti-roll bar does, which is indicated here, is that suppose let us say the right wheel hits a bump, it is going to go up, right, and due to the location of the anti-roll bar and its orientation, this vertical motion of these links is going to result in a twist of this anti-roll bar. And what is that going to do? The anti-roll bar has some torsional stiffness. Okay. So, it provides a resistance to this twist, so that this wheel is ensured, it is ensured that this wheel stays in contact with the road surface and does not lift off. Okay. So, there is a reaction due to the torsional stiffness of the anti-roll bar to ensure that this right wheel in this figure maintains sufficient contact with the tire road interface. Okay. So, that is the function of an anti-roll bar. So, let me write the main points. So, typically used with independent suspension, since the independent motion of the left and right wheels can result in roll while cornering and traveling over irregular surfaces. Okay, so that is one purpose. And what happens is that, like this anti-roll bar, as the name indicates, it minimizes the roll motion, okay, under these circumstances. Okay. So, it is connected to the suspension units on both sides, okay, and twists when one suspension is displaced with respect to the other, right, relative to the other in the vertical direction obviously. Okay. So, that is the function of an anti-roll bar. So, it effectively it increases the so called roll stiffness or the resistance to roll, okay, as far as the vehicle body is concerned. So, this is one mechanism. Another mechanism which is used in vehicles, with a dependent suspension is what is called as this Panhead rod. So, what is this Panhead rod, right? So, the Panhead rod also ensures that the suspension, right, with respect to the vehicle body does not travel too much from side to side in a dependent suspension while cornering and going on irregular roads. So, it is a very simple mechanism. Let us say we have a solid axle or a beam axle, a dependent suspension. So, what happens is that this Panhead rod, one end of it is connected to somewhere near the suspension unit on the one wheel, right, and the other end of the Panhead rod is connected to the vehicle body at the other end, right. So, if you view it from this, like it is just in the opposite end along the lateral axis, along the lateral direction, right. So, that is a Panhead rod. So, the main objective of the Panhead rod is that it prevents or reduces side to side movement or lateral movement of the dependent rear axle while cornering and on irregular roads. Okay. So, one end of the panhead rod is attached to the axle and the other end is attached at the laterally opposite side. Okay. Of course, attached to the vehicle body at the laterally opposite side. Okay. So, that is the feature. So, the advantage is that like it is simple, it provides that what to say so called stiffness, right, to the side to side motion, right. But one limitation is that like the relative motion of this axle and the vehicle body can only now take place constrained by this rigid rod, right. So, for example, the axle must travel in an arc if the vehicle body is displaced, like it has to travel in an arc as constrained by the length of this panhead rod and vice versa, right. So, that is the constraint imposed by the panhead rod. Okay. So, these are different components as far as a typical automotive suspension is concerned. So, the next topic like which we are going to look at is do a simple analysis of the suspension system, right. So, having looked at what are all the functional requirements of a suspension system, how they are realized and how they are classified and what are the features of each type of suspension. So, let us use basic dynamics like to analyze the response at least from one perspective. So, what we are going to do is essentially look at how one can do ride analysis of suspensions, right, using what is called as a quarter car model. So, as the name indicates, a quarter car model like considers like one suspension unit in a 4-wheel vehicle, right. So, so if you have 4 wheels, a single unit 4-wheel vehicle, right. So, it considers one suspension unit in a 4-wheeled vehicle. So, let us look at a simple schematic, and there is something which like the derivation of these equations is pretty straightforward, and that follows from dynamics, like that is about it. Okay. So, if we look at this schematic like of this quarter car model. So, it is a 2 degree of freedom model. So, let me explain what this model is. So, the entire mass of the suspension which is supported on entire mass of the vehicle body which is supported on the suspension is what is called sprung mass, right. So, that is something which we have already defined. So, let us say the sprung mass is ms and the unsprung mass is mu, okay. And let the displacement of the sprung mass from its equilibrium state be Zs, the vertical displacement, right, and let the vertical displacement of the unsprung mass from its equilibrium state be Zu, and Zr is the road input, right. The road there is an input that comes due to the road profile, at the tire rod interface. So, that is ZR, and KT is indicative of the tire stiffness in the vertical direction, and Ks is the suspension stiffness, right, the stiffness of the suspension spring. Bs is the suspension damping. So, this Fa without loss of generality, what we will do is that, like, let us consider an active suspension which has an actuator to deliver an force, right. So, if we have an active suspension, we have an actuation force or an actuator force that is placed between the sprung and the unsprung mass. Okay. So, let us consider that Fa is the force that comes out of this actuator. Okay. Of course, Bs is suspension damping coefficient. So, if we were to draw the free body diagram of this sprung mass and the unsprung mass, we would get the following. So, if we draw the free body diagram of the sprung mass Ms, so what are the forces acting on it? We would have Ks times Zs minus Zu, which is the restoring force from the suspension spring. Okay. Of course, Zs, Zu and Zr are functions of time. In this free body diagram, I am suppressing that function of time symbol, just to because of space constraints, right. And the force from the damper is going to be Bs times Zs dot minus Zu dot. Okay. So, we are considering a linear spring and a linear damping element, and without loss of generality, let us assume that the actuation force Fa acts upwards on the sprung mass. Okay. So, similarly, if we were to draw the free body diagram of the unsprung mass, what would we have? We would have the same restoring force from the suspension spring now will be trying to pull up the unsprung mass. Okay. So, and the damping force will also be acting now upwards on the unsprung mass, right, and this actuation force will now act downwards on the unsprung mass, and there is a restoring force due to the tire stiffness which will be acting in this manner. So, that is going to be having Kt times Zu minus Zr. Okay. So, that is going to be the restoring force from the this tire stiffness term. All right. So, now what are the 2 degrees of freedom of this what to say quarter car model? They are nothing but the vertical displacements of the sprung mass and the unsprung mass. So, those are the 2 degrees of freedom. So, there is Zs n which are indicated by Zs n Zu.